All right, algebra students, today we are going to learn how to solve quadratic equations that have imaginary or complex solutions. This will involve us learning about the fundamental theorem of algebra and using a factoring method called completing the square. Okay, let's clear our work surface, and what we will do is consider the following quadratic equation: x squared plus 6x plus 11 equals 0. Okay, that's an equation. It's a quadratic equation, and the question is, what do we do with this? Well, what we could do first is graph this and see what it actually looks like. And that's actually what we're going to do. We are going to graph this and see what it looks like on the graphing calculator. So on your graphing calculator, make sure you clear the memory. I'm using a TI 84 Plus C Silver Edition. And let me show that calculator. From this, let me make this bigger here. From this screen, once you've cleared the memory, go to y equals and type in the equation of the quadratic, just the x squared plus 6x plus 11 part. So we'll type in x squared plus 6x plus 11. And let's just graph it and see what it looks like. Okay, so we've graphed it, and based on what we have learned so far in algebra, at least when I ask my students how many solutions are shown in this graph, the answer came back 0. There are no solutions, because what the student said is this graph never crosses the y-axis, and because it doesn't cross the x-axis, because it doesn't cross the x-axis, and as a result it has no x-intercepts, then it can have no solutions. And here's the thing, we are going to learn something today called the fundamental theorem of algebra that's going to give us some reason to doubt our initial assumption that this quadratic equation has no solutions. But I wanted to show this to you now so you could see kind of what is going on with this function. This is what it looks like as a graph. All right, now let's go back to our work surface. And let's prove to ourselves that this function is weird. Okay, what do I mean by that? What I mean is it can't be factored in the normal way. Well, how do we factor in the normal way? Well, let's create a little sidebar. Let me go up here and create a little sidebar. This is a test to see if we can factor this thing using the normal factor method that works for a lot of quadratic equations. So if this were factorable in the normal way with whole numbers, then you would be able to find two whole numbers that add together to equal the middle term of the quadratic equation, which is 6, and those same numbers would multiply together to equal the y-intercept in standard form, or the last term of the quadratic equation, which is 11. Well, how do we find out if that's possible? You take 11 and you write down all of its factors. Now 11 is a prime number, So it can just 1 times 11. And then I hear somebody in the back saying negative 1 times negative 11. And that's a clever person. Okay. Unfortunately, neither of these factor pairs help us at all, because while they both multiply together to be negative 11, when we add them together, you get 12 for the first pair and negative 12 for the second pair. In other words, there's nothing that can go in here, and this doesn't work, and so this whole method doesn't work. And a lot of students think that because this didn't work, and because the visual graph showed no x-intercepts, that must mean there are no solutions. And we're about to prove that that is against the law, or at least against the law of mathematics. And that requires us to learn something called the fundamental theorem of algebra. Now, to anyone watching this video whose experience in algebra exceeds 1 semester, I want you to take a break, relax, and realize that I am simplifying the fundamental theorem of algebra quite a bit. So this is neither complete nor comprehensive, but it is going to be just enough to be useful for students who are barely learning how to do this. So here is the fundamental theorem of algebra. Fundamental theorem of algebra says every equation has, at a minimum, a number of solutions equal to the highest exponent. Okay, what does that mean in plain English? What it means is the highest exponent shown in this quadratic equation is 2. So that must mean that at a minimum, according to the fundamental theorem of algebra, there should be at a minimum 2 solutions. Remember, our intuition and our visual analysis of the graph shows no solutions. So something is going on here that we can't see, or that we don't understand very well. And that's true, and we are about to unpack that. We are going to use the method called completing the square in order to factor and solve for this quadratic equation. So we're going to be using completing the square. And I'm so excited to present this to you here today using this visual method that we're going to use, because when I was taught this, I wasn't taught using any pictures. And I'm somebody that learns well with pictures, and maybe you're also somebody that learns well with pictures. I've never seen someone teach completing the square this way until while I was in school. It was only when I turned to YouTube that I learned that this was possible, and to me it makes a heck of a lot more sense than the dry way that I was taught. So, to complete the square, here's what we're going to do. We're going to draw. Draw yourself a square, and it doesn't have to be a work of art. It doesn't have to be mathematically precise. Just draw a square. Okay, we're going to call that a square. The side lengths of the square there's one quick thing we need to do first. So before we can start this process right here, we need to subtract the 11 from both sides just to get him out of the way. So the 11 needs to be subtracted from both sides, and you just need those x terms by themselves. So you got x squared plus 6x equals negative 11. Okay, sorry about that. So here's what we're going to do. We are going to draw shapes to represent these two terms, x squared and 6x. So my first shape is going to represent x squared. And how would I create a shape with x squared? What it means is the area of this shape is going to equal x squared. So what side lengths would multiply together to give me x squared? Well, x times x. X times x is x squared. You know, if you need a quick brush up on that, we have x raised to the first power times x raised to the first power equals x raised to the 1 plus 1 power, which equals x squared. That's what's going on there. Okay, so back to our shape drawing. So I've drawn x squared. The area is x squared. Now I'm going to draw a shape whose area is 6x. So right next to the square, I'm going to draw another shape with a height identical to, oops, kind of bled out there, a height identical to the first shape, but with a rectangular width. In other words, a width that is different from the first shape. Okay. The pen kind of bled out on me there. Okay, so the width here is 6, and the height is x. So the inside here, the area is 6x. Okay, now the next step requires us to split this smaller rectangle in half, just like that. We're going to divide it in two pieces, two identical strips lengthwise. So if the width is 6 and I split it into two pieces, my new little tiny strips of rectangle will each have a width of 3, because that's half of 6. So the area of each of these little rectangles will be 3x. Let's just draw it all again so we get a clear idea of what we're doing. So what I'm doing is I am drawing my square again. And then next to it I'll draw a small rectangle. Okay, and what I'm going to do is imagine that I take a pair of scissors, okay, and I cut that little strip of paper there into two equal pieces. And I put one strip here with the width of 3 and a height of x. Okay, here, this is that square that was x squared. A width of 3 and a height of x. And then the other little strip of paper I place underneath the square so that it has a width of 3 and a height of x, only it's laying on its side. Right? Again, it's harder to explain, and it's more obvious visually what I'm doing. So again, this has the width of 3, okay, and the height of x, but it's turned over on its side. Okay, so now we're going to actually do the completing the square part of completing the square. If I were to draw this shape, if I were to push together these strips of paper, so where there wasn't any blank space between the shapes, I would have a shape that kind of looked like this. I just want to give you the visual intuition of what you're doing. Okay, I have something like this. There's a little piece missing in the bottom right. You see that here? There's a little piece missing down here that would complete the square. And that thing, that is in fact a square, that little piece down there. Okay, now I'm going to draw this. We need to find the dimensions of this little piece of paper. Okay, what are my dimensions of this little piece of paper that is going to fit in here to complete the square? So what are the dimensions? Well, remember, the width here is 3 and the width here is 3. So the width of each of the 4 sides of this little tiny square is going to be 3. Okay, so this is going to be 3 times 3. So the internal area of that little square is 9. Right? What you do with that 9 is you add it to both sides of your equation, just like that. And we'll rewrite the equations now to show what we've done. Got x squared plus 6x plus 9 equals negative 11 plus 9 is negative 2. Now the beautiful thing about doing this completing the square method is on the left side we have created for ourselves something that can be factored into a perfect square. So what I'm looking for is a number that when added to itself equals 6 and when multiplied by itself equals 9. Okay, so let me just make sure that that's clear visually. When it's added to itself, it equals 6, and when it's multiplied by itself, it has to be the same number, it's going to equal 9. Now some of you are already getting it. That's 3 and 3. 3 plus 3 equals 6. 3 times 3 equals 9. Positive 3, okay? So, and if you didn't know that, okay, if you couldn't think through that way, it's also going to be equal to this number right here. So you can get that 3 from various places on our completing the square work. Those 3's were showing up. All right, now you know why that they were there. So we have x plus 3 times x plus 3. Now, what's about to happen, we need to set this equal to negative 2. What's about to happen is I'm about to rewrite x plus 3 times x plus 3 as a single term squared. And I don't want to leave anyone behind when I do this. So over here I want to make a joke. Okay, I want to make a point. You guys know I'm a tremendous artist. Okay, and as a tremendous artist, I'm going to draw Harry Potter. Okay, he's got the little lightning on his forehead. Right, here he is with his broom. Harry Potter times Harry Potter equals Harry Potter squared. Okay? In the same way, x times x equals x squared. In the same way that blob times blob equals blob squared. So let's go back over to our real problem. I have something times itself. Okay, here I had Harry times Harry. x times x, blob times blob. Now I've got x plus 3 times x plus 3. So I'm just going to write x plus 3 in parentheses squared. So that's all I'm doing. I'm simplifying. So I don't have to write x plus 3 times x plus 3. I'm going to write x plus 3 squared. And that's literally what it means. Let me just make sure that this is super clear. X plus 3 squared can be broken down into two parts. X plus 3 and x plus 3. So that's all I've done. I've just rewritten it. Now, so some people are looking at this saying, why is this guy spending so much time on this? Well, there was some confusion in class, so I want to make sure that this is very clear. So I've got x plus 3 squared, and I'm still bringing down negative 2, equals negative 2. Okay? Now, what is the opposite operation from squaring something? If you can't remember, think about what part of the plant is a carrot. It's the root. So we're going to take the square root of both sides. Okay, we're going to take the square root of both sides. On the left side, when I take the square root of something that is already squared, what it has the effect of doing is just getting rid of the square number, the squared term and the radical sign. So all you're left with on the left side is x plus 3. On the right side, I have to stop and think for a minute because I'm about to take the square root of a negative number, which even if we don't quite know what we're doing, we should stop and think there has got to be some kind of rule there because you can't typically take the square root of a negative number. So how do we take the square root of a negative number? Well, I'm glad you asked. I'm so glad you asked me that. Let's go back up here. And beneath the fundamental theorem of algebra, let's write this. This is almost equally as important as the fundamental theorem of algebra. It's actually part of the fundamental theorem of algebra. The square root of negative n, where n is some number. Okay, so in our case, n is 2. So the square root of negative 2. The square root of negative n is equal to this plus or minus the square root of n, positive n, times I. So plus or minus the square root of n times I. And the reason that's the case is because the square root of negative n can be rewritten as the square root of negative 1 times n. And that, in and of itself, can be rewritten as the square root of negative 1 times the square root of n. And this is a key point. This is one of those things you just have to know. The square root of negative 1 has been determined by mathematicians to equal the imaginary number I. So whenever you find yourself with the square root of negative 1, you replace it with an I. So what we did here is we took negative n, broke it into two pieces, negative 1 times positive n, split up the square roots, square root of negative 1 times square root of n, and then we wrote this. The square root of negative 1 equals I. Therefore, that's what those three dots mean. Therefore, the square root of negative n equals the square root of n times I. Okay, which can be written as square root of n I. Make sure to put that plus or minus. I forget that all the time as well. Plus or minus the square root of n times I. Okay, this is important. Okay, we'll let that sit for just a minute, and then we'll go back down to our problem. We were taking the square root of negative 2. Remember? Well, the square root of negative 2 is equal to plus or minus the square root of positive 2 times I. All I did was I substituted 2 for n up here. All right? Now the last thing I need to do is move my 3 to the right side. And on the left side, the 3's cancel, leaving x by itself. X equals plus or minus the square root of 2 times I minus 3. And what people are wondering about is they said, hey, I thought there were going to be 2 solutions. I thought you said fundamental theorem of algebra said there were going to be 2 solutions. Well, okay, there are. It says plus or minus right here. Okay, so I've got my first solution, x1, equals positive square root 2 times I minus 3. And my second solution, x2, equals negative square root of 2 times I minus 3. These are the 2 solutions that our theorem predicted would be there. And here's the thing. These solutions are composed of 2 parts. They are composed of a real part, which in this case is negative 3, and they are composed of an imaginary part, or a complex part, which in the top one is positive square root of 2 times I, and the bottom is negative square root of 2 times I. So those are the 2 solutions, and they're complex solutions because they contain real numbers and complex numbers. Now listen, when I was taking algebra, and we learned about this, all this stuff. First of all, we never got the graphical representation of completing the square. So this makes a lot of sense to me when, if you didn't include that, it wouldn't. Second, I was never told what this means visually. So I want to show that to you today in an effort to make you understand something that I never understood until I was old. So what I want to do is bring up I want to share my screen with you and bring up this cool online 3D surface plotter. All right. Now let me show you something here. I'll include a link in the description to this, but it's if you scroll up this page, you can see what it is. 3D surface plotter. I think if you Google Academo or Academo 3D surface plotter, you'll find this tool. I think I zoomed out too far. All right, let me swivel this thing around until I've got the x-axis and the y-axis more or less the way that we know them and have grown to love them. Okay, now I'm looking at it. My x-axis is on the bottom, and my y-axis is plotted vertically. So that looks like our graphing calculator. Now, over here, under expression, I'm going to type the equation we've been working with so much. X squared plus 6x plus 11. Okay? And I set the ranges here at -30 to +30. And just hit calculate. Now, what you're looking at is a three-dimensional plot of what our calculator only showed in 2 dimensions. And what this is representing to us is the 2 dimensions of the coordinate plane, x and y, and then a third dimension that we call the complex dimension or the imaginary dimension. And this makes a lot more sense when I do this. It's almost like I'm taking the calculator and I'm laying it down, but while I lay it down, I'm going to reveal that there was actually a third dimension to our graph. And that's what I'm doing right now. So now what essentially is shown here is I have laid the graph flat and I've shown the x-axis horizontally, the y-axis kind of going into the screen, and then plotted vertically is this z-axis, which is representing the imaginary solutions of my quadratic equation. And so what this is demonstrating to us is that there are solutions to our quadratic equation. Now this whole 3D chart thing kind of simplifies the matter, but it does bring it home that there was something that was not visible to your calculator's eye when you first took a look at this function. Okay, it looked like there were no solutions, and yet here we are looking at a three-dimensional shape. So I just kind of want to leave this tutorial on this kind of moment of awe as we look at this thing that is totally invisible if I flip it up like this. You cannot really tell that there's a three-dimensionality to this shape. And your calculator, unfortunately, cannot plot in 3D. So you can't do this. And it's really neat to be able to see it like this. Again, I'll include a link in the description. And you can play with these yourself. It's fun to play with. So let's flash back to our screen. Hide and show the work surface again. And just kind of take stock of what we found. We found that by completing the square, we could take this quadratic equation and we could factor it by completing the square, take the square root of that perfect square factor, then also take the square root of the constant on the other side of the equal sign, and that we would end up with exactly 2 solutions, both of which have a real component and an imaginary or complex component, making these 2 complex solutions. We also learned the fundamental theorem of algebra, a kind of reduced and condensed and simplified version of part of the fundamental theorem of algebra. Every equation has at a minimum a number of solutions equal to the highest exponent. Okay? Again, there's some people with a PhD in mathematics whose heads just exploded, but that's okay because I'm not talking to you. I'm talking to freshman Algebra 1 students. Now, finally, we talked about taking the square root of a negative number, and that when we take the square root of a negative number, we're really pulling out a square root of negative 1, and their mathematical gods, okay, have determined that the square root of negative 1 is I. So the square root of any negative real number is equal to plus or minus the square root of that number, positive, times I. So in our case, that was the square root plus or minus the square root of 2 times I. Okay, in this case we subtracted 3 from both sides. And those are our two complex solutions. So I hope this whole tutorial was helpful. We got to complete the square and learn about theorems and graph things and look even at a 3D model. And it was very cool. So I hope that this was helpful. Please make sure to like and subscribe and hit that notification bell so you are alerted every time I publish a new video. Thank you.